And we have a starting point, which is 3, 2, right here. And then we have a final point, which is 5, 5, which is right here. And then we want to put a line through it, okay? Say our line, we want it to go through in that direction. Line in blue color. How do we parameterize this? Is the question. Okay. First thing we can do is point slope form, because the slope right here, I'm gonna do it with that color now. So this way, delta x is equal to 2, and this way, delta y is equal to 3a. So my slope, of course, which is delta y over delta x, is equal to 3 over 2. And then point slope form will tell you, say this is our starting point, is equal to y minus 2 is equal to 3 over 2, and then x minus 3a. Let me write that in a slightly different way. And if you notice, this is our symmetric equation, isn't it? How about that? Now, does that remind you of something ellipse looking thingy? By the way, like x squared over a squared plus y squared over b squared is equal to 1 kind of thing? Even better, I'm not sure if I talked about this, but suppose we have, say, this. What's the equation of this, really quick? Believe it? It is now, isn't it? Oh yeah, everything looks kind of like this, eh? Okay, anyway. Oh, by the way, this notes, before I take it out, if you want to document it, you go to the Teams notebook and you can actually print or convert it into PDF form. Then you can just keep all of it, those of you who like keeping these kind of stuff. I personally don't. And this, now we come back here. So the way we figure out parametric equation is just this then. Because they are both equal to t, so they must be equal to each other. And this thingy tells you x is equal to 3 plus 2t, and this thingy tells you y is equal to 2 plus 3t. This is our parametric equations. Okay, but can we just feel it? I mean, why have it so complicated when we can feel it? And our point is 3, 2, look at it as a motion of a particle. All of you are hopefully taking physics right now, right? So let's say we want to go from coordinate 3, 2 to 5, 5 in 1 second. Well, then you start with coordinate 3 and 2, and 1 second later, so when t is equal to 1, you want these coordinates to be 5, 5, so you put 2 here, 3 here, so that works. You see how fast and easy that is? And even better, has your physics teacher taught you this yet? Yes, no, maybe?
Your screen is lagging for me, so.
What? Screening you what?
The screen is like lagging for me, so.
Yeah, I'm experiencing the same thing as well. It kind of like freezes for like 30 seconds and then, or maybe like 20.
School Wi-Fi is crap, huh? I'm in my classroom, but this Wi-Fi, Let me try changing. Uh-oh. Are you guys there?
Yeah.
Yes.
Yeah.
Because I don't have internet connection. How are you still there?
Are you on a different
This
computer
is-
as well? Or
No, it's my Surface Pro, same Surface Pro. But it says no internet connection. Oh, actually now I have it. But it's like in and out. It's really weird. Okay, as long as you're there. That's why it's laggy and weird. Okay. Have you seen this thingy from your physics class yet? Okay, so you've
Yeah.
seen it, right? Why don't we expand this into vector equation? Oh, wow, now one notice. R of t is equal to R at 0 plus V. And eventually, not for now, eventually it's gonna, you know what I'm saying? You seen this before in your physics class? Yeah, but for now, then it gets curvy. But for now, let's just do this. So we need the velocity vector, and velocity vector is just this much, isn't it? V, and that's just change in x and change in y, so that's 2, 3. So if we plug that in, so we have our own initial point, which is 3, 2, plus our velocity vector 2, 3, t. And of course, this becomes 3 plus 2t, and then 2 plus 3t. Lo and behold, this is our x and this is our y. So we want to think like this, okay? Particle motion in time, in space-time. You get it? X and y is space and t is time. Okay, and then we can build this thing into actually 3D, right? All we need is our original position and velocity vector. Okay, but that's how you were taught in pre-calculus, and that's how I taught you last year. But I want you to notice something, and this is huge. When we say this is a vector right here, right? What does it mean? This thing being a vector really means this position vector. That vector. You know what I'm saying? And then, well, then we have another position vector at 1, which will look like this. So R at 0 looks like this, and then R at 1 looks like this. So think of it as this arrow, tail at the origin and moving through this line. You get it? It describes the motion in space. And this is a big concept later when we get into 3D vector function. Okay, that's what vector function is. It describes the motion. This arrow, tail is always at the origin, okay? Okay. Am I hearing my own voice?
I can't really deal with this, Champ,
1v1 this guy, but I can't 1v1 this guy with this guy and this guy hitting me, right? I can easily 1v1 either of these guys.
What is this? Okay, mute yourself. Children, mute yourself. Okay. Now, then, can we talk about the cycloid? Do I want to talk about cycloid today or tomorrow? Time-wise, we have time, right? The period ends at, what time does this period end?
12:10.
12:10.
12:10, right? So yeah, we have time. We have plenty of time. Okay, let's talk about cycloid. We kind of talked about it last year, but hey, cycloid is this, right? If I roll this, and we have to derive the equation of this, because your project is to figure out epitrochoid, right? Okay, and you have to present, and we'll do it in group of, we have 16 students here, so group of 4, how's that? 4 different groups, and then you actually get to present over the team. So you see everything has to be virtual, electronic, and everything. Oh my God, and anybody has a right to say no to anybody. So talk to each other, bribe each other, buy pizza. Oh, you can't even get together and buy pizza. Bribe each other somehow. Okay. And here is what you are deriving. Ready? This thingy up here. You know what I'm saying? And then you have to make a PowerPoint or some kind of presentation. And you have to present it to the class. I will enable your presentation feature on the team. And then 4 of you have to know how to do this. Okay, that's coming up. I have to update the dates, but this coming up sometime soon. Okay. And one more thing, you see this thing only just comes down here in this, but I want this to dip below. So if I stop rolling and go back to this, I want this thing to look like this. You know what I'm saying? And the name of that curve is called epitrochoid. Okay. Now you're thinking, why anybody want to do such a thing, right? Might be Copernicus. No, actually, a long time ago when they used to believe that Earth is the center of the universe, right? And then sun evolves around. So here's the sun around the Earth. And there are weird stars in the planet, big, bright stars. That does not really just go around, but it's just like shows this kind of weird pattern. So they named those stars after gods, such as Jupiter, Saturn, Neptune. You get it? Venus, Mars. And if you think about it, if you put Earth at the center of the universe and sun evolves around the Earth and planets evolve around the sun, then you will have this kind of motion. And somebody has figured out the equation of this to study the planetary motion. Of course, later, if you put the sun at the center, that simplifies things quite a bit. Okay, so there's that historic background about this thing. Okay, so let's figure out the equation of cycloid so that you can use this idea and figure out the equation of epitrochoid. So Suppose there is a axis like this, and then we have just the, how do I make it? Oh yeah. We have this thingy, wheel rolling from here. Let's say we came about here. I want to make it bigger. Okay. And that pen that was at the bottom is going to come out about here and then make that point. You know what I'm saying? Okay. I think we did this last year, so you kind of know, right? Do you at least remember forgetting? Okay, so this, let's say, is R. Okay. And then this thing is rotated that much. So we'll call this thing T, our angle of rotation. Theta, T, whatever, our parameter, T. Okay. And Y is, I over-rotated it. I want this rotation to be not, oh, that's surgical. Let's say it's only about went that way, okay? So we can see the triangle. And I want to care about this triangle. So this is my Y. Is when we say coordinate X and Y, that means this much is X and this much is Y now, isn't it? This is Y. So is my Y is easier, so let's do Y first. I'm gonna do it at the top. Is my Y same thing as R minus, and then this length right here, which I'm gonna put it, this length right here. And this is also R now, isn't it? In this right triangle. So is that R cosine T, eh? So Y is equal to R minus R cosine T. Common factoring R, so you have 1 minus cosine T is the Y coordinate. And X coordinate, of course, is this whole thingy, whatever the hell, this whole thingy, minus this part is R sine T, isn't it? So somebody tell me, what is this whole thingy? Come on, we've seen it before. Wow, wow, wow. All this distance learning has just fried your brain. Oh, staying home too much, eh? Dang. Okay, here's a big hint. I need another color. This distance right here and that one right there has to be same, right? Because wheel just rolled. So how much is this arc length then? This arc length.
Isn't it RT?
RT is correct, right? R theta, arc length formula, R theta. You want me to derive that again for you? Are you sure you know that's R theta or RT for us? Okay, well then I think we have it. So our X coordinate is RT minus R sine T, eh? Common factor R, so you have R and T minus sine T is the equation of cycloid. Okay, this is basic idea and you have to convert this into epitrochoid. Of course, all of you will Google it, but hey, at least in the previous years when kids were in the classroom, by the end of this period, there are some kids who put this thing on their calculator and showed it to me, like at the end of the period. Those are the ones that you want to bribe to be your teammate. And then, of course, you need to, of course, recruit somebody who's savvy with computers because you have to present it over, right? You don't have to divvy up the slide and then present it that way. If one person, and then you, of course, need somebody with a beautiful voice and face. Oh, I'm so sorry. But okay, who can see? You can do different things. So it's unlike most teachers. Oh yeah, you take this first quarter, I take next. You don't have to do it. If one person talks from the beginning to the end and one person does the tech thing and one person does math, that's fine. And then of course, number 4 used to buy pizza, except coronavirus is just killing us all. Okay, you get it? Okay, so you have some recruitment to do. Now let's talk about coordinate system. Okay, 3D coordinate system. Let's see if this thing is any good. I don't like it. I really, really hate it. Forget it. Forget it. I'm going to just hand sketch. Okay, 3D coordinate system looks like this. This is X, Y, and Z. Okay, another option, depending on what you're sketching, some people do it this way. Okay, this is known as isometric. It's the second one. Whichever floats your boat. And I actually go interchange between the two, depending on what I'm. If I'm in a Cartesian coordinate, I tend to go with this. If I'm in a polar coordinate, let's just say that because there are 2 different polar coordinates in 3D, then I tend to go with this. Okay, so I'm gonna sketch both of them. Okay, say Cartesian coordinate first. I'm gonna get rid of this now. Cartesian is easy. Say X, Y, Z coordinate, right? Say if your X coordinate is somewhere here, and then your Y coordinate is somewhere. This is your usual XY. You know what I'm saying? And I'm going to call this X, Y, 0. This our Z coordinate is 0. And then we go up. So it's a bunch of parallelograms. You know what I'm saying? So this is X, Y, Z. So we used to have X and Y, but now we elevate and give a Z. So we are in 3D. By the way, this class called the multivariable calculus is also known as vector calculus, also known as 3D calculus. Okay, in chapter 11 is the only chapter we'll stay in 2D, and after this we take off and fly. Okay, in 3D, and everything else will be done in 3D. So this is how you do the Cartesian coordinate. You know what I mean by Cartesian rectangular coordinate X, Y, Z, right? What's the name of the mathematician who gave us Cartesian coordinate?
Descartes.
Descartes, who famously said, I think, therefore I am. Yeah, that guy. He gave us this Cartesian coordinate, so that's why we call it Cartesian after Descartes. That's easy enough to see, right? Well, then let's talk about the polar coordinate. Except, what do you mean by polar coordinate in this business? You know what I'm saying? Polar coordinate is not as easy. Which one are we talking about? Right, so there are a couple of different polar coordinates. Okay, I'm gonna sketch it. Why is it not working? Really? I'm gonna use this. I need an ellipse. Huh! Idiot computer. I need an ellipse. Then from here, I'm gonna have z-axis like this. And then I'll put y-axis this way, x-axis this way. You know what? I changed my mind. I'm gonna put y-axis more that way. So this XY plane is our usual XY, and this is our usual polar coordinate. You know what I'm saying? So if you have a point here, that's our usual R theta and 0. And this is our theta right there from x-axis. You know what I'm saying? Say yes. So do you remember x used to be R cosine theta and y is equal to R sine theta? Now we give an elevation. That's C. Like that. You get it? So this point here is, so Z is equal to just C. So this point right there is X, oh, not X. I'm gonna put it in different colors so you can see that coordinate right here is R theta Z. So this is pretty simple. It's just our regular polar coordinate on XY plane. And then we just give an elevation and just C, literally. Good? Say yes. Okay, what's really confusing is the spherical coordinate. What? Okay, let's put spherical coordinate down. I need a circle, so let's do this. Hopefully, oh yeah, that worked out. And then I'm gonna throw the axis. This time I'm gonna put isometric view. It looks like this. Okay, then there is the regular. You know what? I'm gonna put this thing a little bit on a. I'll go sideways today. Easier to see this way. So there is this point right here. So this is regular theta and this is R. So far so good? So like before, this thingy right here. Okay, this is what we call X here. And this is Y, isn't it? So far, X is equal to R cosine theta and Y is equal to R sine theta, just like before, polar coordinate. You with me? And then I'm going to erase that Y because it's going to be confusing. I'm going to put Y here. Then we give an elevation Z like this, same as before. So this much is Z. Like that, right? However, this thingy called the spherical coordinate does not have R and X and Y. It has this thingy. This thingy is called rho, not P. It's a Greek letter rho. What is the English equivalent of rho? Take a wild guess. Greek rho equivalent is our R. Get it? Because R was already taken. So this is rho. And so this coordinate is called rho theta and phi. Yeah, we know what theta is. What the hell is phi? Phi is that angle right here. Ooh. Ooh. That's very difficult to understand now, isn't it? Think of it as a crane operation. Oh, I need to. Well, this is when I need you in here to show you how this thing works. But okay. So just bear with me and let's just think about this. Is this also R in that triangle? In this right triangle? Say yes. So do you see that R, well, do you see that, yeah, R is equal to rho sine phi? And do you also see that Z is equal to rho cosine phi? Remember, Z is this thingy. Do you see that triangle, or you want me to sketch that triangle separately? Then all we have to do is substitute. So we have R, which is rho sine phi. So we have rho sine phi cosine theta. And here rho sine phi sine theta. And our Z, like I said, is rho cosine phi. This is the relationship between Cartesian and spherical coordinate. Holy cow, huh? And one of the benefit of having spherical coordinate, of course, is when you have something circular. Wait, did somebody just join the class? Oh. Jackson, you got cut out? Okay. Is this? Well, I'm just going to copy it off of the notes that I have in Dropbox, because otherwise it's very difficult to sketch this thing. So hold on. I'm going to paste it here. Okay. Do you see that surface on the sphere and our rho varies from here to here, and then that it moves that way and it moves that way? That's called ds, let's call it surface, dA. And then do you see that this thingy, I'm going to put it in different, this thingy is the arc length. So that's R. Let's not call it rho, because rho is a variable. This thing is a capital R, which is the radius of the sphere. Then do you see that is R d theta? I mean R d rho, d phi. Okay, and then we want to know this arc length, which is same thing as that length, right? And this is not on the surface. This one is not on the surface. Only that part is on the surface of the sphere. It's like confusing, but can you see it? So that thingy is R theta right there, isn't it? Do you see it? Our regular polar coordinate R theta. Polar coordinate just continues in like that. And R theta, of course, R theta. Oh, lowercase r theta, because uppercase R is really out there, right? Our variable R, and R, remember, was rho sine phi, and then R theta. Oh my God, I'm really getting R d theta. And the theta. So far so good. But then we are not calling this rho, we are calling this is constant, we are just calling it capital R, aren't we? So our ds is R d phi times R sine phi d theta. Are we good? Are we good or not? Okay. Having said that, why would that be so much beneficial? Watch this. Your surface area. Okay, you don't have to worry about this. This is like chapter 16-ish, but I just want to give you a little preview of where this class is going. Of that, the S, which will say R square sine phi, the phi, the theta, and phi will vary from this vertical z-axis when phi is equal to 0, and this thing comes down all the way to the other side. So that's from 0 to pi, and theta is our usual 2 pi, 360 degrees. I'll give you a minute to swallow this. Can you swallow this? Okay, we have chapter 16 to recover this, but just watch this. And this integral, you do it from inside out. R squared is constant. And then what's the integral of sine? Useless kids. Right? And then we just evaluate it. Does that give us 2? And that's 2 and just theta, isn't it? Jackson keeps getting cut out. And that, of course, gives. Dang. How about that, huh? You see where this class is going? I will not really do the other one. I'll just show you, because otherwise this is like too overwhelming. But and then, of course, volume of a sphere, we do it with triple integral. Hopefully by the time when we get to this, at least most of you will be back in the classroom, so I can use my hand to show you what this. It's really difficult to see this and imagine it on your computer screen. Any questions?